How much electricity do I use? When considering installing a solar system, you need to fully understand how much electrical energy you use. In this lesson, we're going to start by looking at electrical terminology so we better understand power and energy. We're going to discuss a few of the appliances that we might see in our homes and how our electric bills become calculated based on appliance use. We'll look at some of the pricing structures for electrical bills that we see around the world and talk a little bit about energy efficiency and how we might be able to reduce the energy we use before we invest in solar. The first thing we want to talk about here is power. The units of power that we use is watts. And so power is the rate of electrical energy, either generated or consumed. All devices are going to have a rating in watts on them. In this case, we see a light bulb example as a 50-watt light bulb. We would also see watt ratings on our solar modules. All of our solar or PV modules are based on how many watts they produce at certain conditions. So the unit of power being watts, that is this rate of electricity that's a constant, either going in or out of the device. Our homes are going to draw X number of watts or kilowatts. Our solar electric system is going to produce watts or kilowatts. And so power is this rate of electrical consumption or production. So watts being the base unit, as we go up from watts, if we have 1,000 watts, we have a kilowatt. And so we go from watts to kilowatts, kilowatts to megawatts, and megawatts to gigawatts as we increase the amount of watts or the amount of power that we're either producing or consuming at any given moment. Now the next unit we want to look at is energy. So energy is the total work that is performed, either the total amount of production of energy or consumption of energy. So energy consumption is really watts over time. So we're adding the time component. So it's like power times time. So the unit that we use for energy in the electrical world is what we call a watt hour. So how many watts for how many hours? As that gets bigger, of course, that builds up to a kilowatt hour. So if we look at an example here, we have a 50-watt light bulb, and 50 watts is the power. Okay, so that's a constant 50 watts whenever that light bulb is on. Now in this example, if we have a 50-watt light bulb that's on for 3 hours, it's 50 watts for 1 hour, 50 watts for 2 hours, 50 watts for 3 hours. Then the question is, what's the total amount of energy that has been used? So power times time, or watt hours, we end up with 150 watt hours. So it's a 50-watt light bulb for 3 hours of operation is 150 watt hours that's consumed. That's the amount of energy. So as we go up, of course, from watt hours, we go to kilowatt hours or megawatt hours or gigawatt hours, depending on the number of watts and how we, how big the units get. So watt hours, kilowatt hours, megawatt hours, and gigawatt hours are the units that we use to describe electrical energy that's either produced or consumed. Now, if we start to look at some of our electrical loads, we've just selected a few basic electrical loads that we might have in our homes, so we can kind of start to understand how these impact our electric bill. Most electric bills are charged per month. So in this example, we're going to look at monthly kilowatt hour consumption of electricity. So if we look at this first example, we have an electric stove, and we're saying the power or the watts from the electric stove is 1250, so 1250 watts, or 1.25 kilowatts, depending on how we use our units there. So 1.25 kilowatts is the constant running load of the electric stove when it's on. Then the question is, how long do I use that stove or that device or whatever the appliance that we're looking at? Well, the power in watts multiplied by the time in hours gives us the kilowatt hours that we're going to consume per month. So the question really then becomes, how big is the device in watts? How many hours a month do we run it? Means how many kilowatt hours or how much energy do we have to buy from the utility company? So a 1250 watt electric stove that ran for 10 hours would be 12.5 kilowatt hours. Now, of course, the kilowatt hours that's consumed is going to be based on how often you cook and how often you run that stove. As we look through some of these other examples, tea kettle, 1150 watts, how many hours a month do I run it, can give me our energy consumption for that month. Now, things like refrigerators can be a little bit more difficult. There can be a really big range in refrigerator freezer consumption in watts. We're showing here 100 to 600 watts. That's a huge range because over the last 20 or 30 years, the energy efficiency in refrigerators has gotten dramatically better. So the range of watts can be based on a number of things. The age of the refrigerator, how old is it? How well insulated is it? So the newer it is and the more insulated it is, the less power and then energy that it consumes. Now, the other thing with refrigerators is they have what we call a cycle time. So they turn on, turn off, turn on, turn off. And the compressor runs based on how the run time is based on keeping the refrigerator at the set temperature. So some of the other variables here can also be, what is the air temperature outside of the refrigerator? If this sits in a very hot climate, it could run a lot longer to keep the internal temperature correct. If it's in a cooler space, then the compressor doesn't have to run very long in order to keep the internal temperature at our setting. And so refrigerators are hard to calculate their actual watts and energy production. It's the sort of thing that we can measure with certain tools that we could plug in and measure the watts and energy consumption. Or a lot of refrigerators and appliances like this will also give us a monthly or an annual kilowatt hour energy estimate. So the newer the refrigerator is, we should be able to get a monthly or annual kilowatt hour estimate given based on a number of circumstances like air temperature. So those are some of the things about refrigerators. And then microwave is a very simple thing. Say it's 1,000 watts in this example. How many hours do we use it? Something that's a little bit different and more common with electronics is things like our Wi-Fi router here, for example. This is a great example of something that's very low in power. So it's only 40 watts is what it runs for power. So it's low power, but it's a type of device that runs 24 hours a day, every day of the month, every day of the year. So in this example, we say 40 watts times 720 hours per month means 29 kilowatt hours is the monthly energy usage for that Wi-Fi router. So that might be the sort of thing that's not intuitive because these little electrical devices that are much smaller, because they run so long, they can actually produce or consume more energy than some of the bigger devices that we would ever think about. So we need to think about devices like that, not only our Wi-Fi routers, but TVs or satellite dish receivers, computers, phone chargers, all these things that are on or plugged in all the time can draw small amounts of power over a large time to have a greater energy consumption than we might expect. So a number of things to just be aware of. This is how your electric bill adds up. And this is where the electrical company then charges us based on our energy every month based in kilowatt hours. Now, as we go into thinking about if I'm going to design a battery system, okay, so if your application for solar is battery based, either off-grid, standalone, or a backup power type of battery system, we need to do a much more in-depth load estimation. So this is a very basic load estimation table or spreadsheet of sorts. And when we do battery systems, we need to not only know what the monthly total energy consumption is, but we need a lot more details. And so normally we're going to try to get customers to give us as much information we can about the devices that they own. So if they own the items, we want to look up how much they use. If they're going to be purchasing them, we can try to make some estimates. but we want to be as accurate as we can. The problems if we're wrong in estimating our loads here, if we estimate too high and we assume the loads are bigger than they actually are, it's not really a problem from a design perspective, but it becomes a much more expensive electrical system. So if the system is oversized, it's more expensive, but it's going to work great. If we estimate too low, we're going to have a system that's undersized, which means the battery's too small, the solar's too small, and it's going to not meet our needs, which means either we're going to run out of power, or if we have a backup system, the generator is going to run a lot longer than we had expected. So we want to do our best to estimate our loads and to try to get averages. We know things change the way we use devices in our homes or businesses, but we want to try to do the best we can. So if we look at an example here, the first one we have is lights. We have a 10 watt light. Let's say in each light bulb is 10 watts. And in this example, we're saying we have 8 10-watt light bulbs. So our total operating watts for our lighting is 80 watts. Then we have to estimate how many hours a day do we want to run those light bulbs. Now, if this is a small battery system where we're just running, let's say, some street lighting or a very specific load, like say just an independent light, we can set a timer, we can control that. We know that if we're running things like in our homes or our businesses, that might change day to day. So we just do the best we can to make an estimate. So we're saying 10 watts per bulb, 8 light bulbs, gives us 80 watts as our electrical draw. We're going to run 80 watts of lights 6 hours a day, and we're going to do that for 7 days out of the week. So every day we run those lights. And as we calculate this, we're going to take this times 7 days a week and then divide by 7. I'll talk to you more about why in a minute. And then we get into the average watt hours a day of 480 watt hours of lighting loads for that day. Okay. Now let's look at another example. We have a vacuum cleaner here. Now this is a much higher electrical load in watts. It's 500 watts. We have one of them. So one 500 watt vacuum cleaner, our time per day estimate, 0.25 of an hour, which means 15 minutes a day. I'm going to run that vacuum cleaner, and I'm going to do that 2 days out of the week. So we're kind of trying to make some estimates. How long might I run that vacuum throughout the week? So 15 minutes, 2 days out of the week, and that's where we take that 500 times 0.25 times 2 hours divided by 7. And the reason we multiply times the days and then divide by the days of the week gives us an average consumption. And so that says over the course of the week, we're going to average 36 watt hours per day for that electrical load. Now, if we go down, we look at the television, 300 watts. We have one of them. So we run 300 watts of TV times 3 hours a day, 5 days a week, divided by 7, gives me 643 watt hours per day is my average daily consumption. So we're trying to average out those things that we don't use every single day. If we look down a little bit further, we have, clothes washer, computer, phone charger. Phone charger, we're saying it's 7 watts. We have 3 phone chargers that run in the house, gives us 21 watts of total electrical load. And then 7 hours a day, 7 days a week, 147 watt hours. So you get the idea. We want to get the best estimates we can in what we call total connected watts. So if we have everything on at the same time, how many watts would we draw in that building? So the next step is we total up all of these operating watts, 80 plus 500 plus 300 plus 500 and so on. And we come to the bottom where we have 3016 watts or 3016 watts. Now, that number in total watts of our electrical usage helps us start to select an inverter in our system. So we say, how many watts do I need to deliver at any given time into that building? Well, I need to deliver at least 3,000 watts to make sure that I can run all the things that I want to run at any time. So that's how we total up the watts. And then as we come to the far right side and we look at the watt hours per day, we're going to do the same thing. We're going to add up 480 plus 36 plus 43, and so on. And we end up with a total energy. That total energy of 4,532 watt hours, or 4,532 watts or watt hours, or if we changed our units, it'd be 4.5 kilowatt hours. So that's our total energy. That's a number that we need when we start to design systems to understand how big the PV array needs to be and how big the battery bank needs to be. Because if that's my daily energy usage, I need a battery that can deliver that every day. Now, and also, what if I have 2 days of cloudy weather or 3 days of cloudy weather? You know, we talk about what we call days of autonomy. How big of a battery bank might I need? And if I'm delivering that energy from my battery every day, how big of a solar array do I need to make sure I create that amount of energy every day or more? So these different numbers help us size things like battery systems, PV systems, and inverters based on all the different calculations that we're going to do. Now, when we come back to electrical utilities, we talked a little bit about, you know, watts and kilowatt hours, and then our electrical loads for battery-based systems. But if we're looking at grid-connected or utility-connected systems, we need to understand that all utility rates have, or all utilities have rates or tariffs, and those electric utility tariffs can differ in a lot of different ways. So the utility tariffs are based on factors such as the demand and the consumer type. When we talk about consumer type, it means electrical companies can often charge us different rates or tariffs based on is it residential, small commercial, large commercial, industrial, agricultural, government, those sorts of things. Now, of course, we're talking in this training to people from all over the world, so we need to understand utility rates differ, of course, between countries, states, even city by city. And so trying to help you understand the different types of structures out there so you can look at your electrical bill and figure out more about what you're getting charged for electricity and how they charge you based on these different tariffs. So the four versions we're going to look at here today are we call a flat rate, a tiered rate system, a time of use rate tariff, and a seasonal. So we'll look at each of those in a little bit more depth. So a flat rate system basically means the utility tariff is not affected by consumption and it remains unchanged throughout the month or the year. So flat rate just means we have a fixed cost of electricity. No matter how much you use, that is the fixed amount that's constant. So it doesn't change throughout the year. You just pay whatever the set cost is, no matter what time of day, no matter what time of year, or how much you consume. Very easy to calculate that way because you can look at a fixed price and the number of kilowatt hours that you consume. Also easier to estimate the return on investment of your solar because it's all a flat fixed price for energy. So that's a flat rate. As we change a little bit, we have what we call a tiered rate system. So with a tiered rate, the more electricity you use, the higher your utility tariff gets. So what that means is utility companies will give us these blocks of energy. So we see the first one is 0 to 1,000 kilowatt hours as an example, is going to be at one price. And then as we go from 1,000 to 1,400, it's going to be a different price. 1,400 to 2,000 and 2,000 and higher. So these are just some example numbers that will say in these different ranges of consumption, you're going to pay a higher price of electricity as you go up. So that affects your bill, and it'll also affect the return on investment of your solar and how that all gets calculated together. Next thing we're going to look at is what we call a time of use structure. So this means that utility tariffs are lower during off-peak and higher or increased during our peak hours. So if we look at this example here on the left, we're saying weekdays, we have an off-peak, a mid-peak, and a peak rate structure. So as those blocks go up, the price of electricity goes up throughout those times of the day. Some utilities make that for every day. Some utilities will do a weekday and a weekend version. This affects a number of things. We can make decisions on when we consume power. So maybe we save a little bit of energy or save money by using less energy during the peak time. Or maybe we put in solar and we point it more to the west, so we produce more electricity during the peak time to offset the more expensive price of power. There's a number of things we can do when we start to consider those time of use rate structures. The other thing that can happen is we can have what we call a seasonal time of use. So instead of a constant throughout the year, the utilities may vary the price based on season. Oftentimes the summer rates can vary with the utility demand, and a lot of utilities, especially in hot climates, have the highest demand of electricity during the hottest times of the year and the hottest times of the day. So we may see that the summer rates are higher and the afternoon is the highest. So we see this example. We have a mid-peak during the day, and from noon to 6, this higher peak when it's hottest out and when air conditioning is running, not only in our homes, but in businesses and industrial applications as well. Some utilities carry that through the weekend, and some give a reduced off-peak weekend price. So that's a summer rate structure for time of use ratings. We also may see where winter rates might be lower depending on what the demand is on the utility grid itself. And so all these rate structures are based on when the utility grid has the highest demand from the consumer is when the prices go the highest, in order to give benefit for you to use less energy during those peak demand times to try to kind of protect the grid in a way when the utility power is the most expensive. Usually when there's the least amount of it available due to the high demands. So other thing to think about is, even though we're saying summer and winter here, there are many utilities out there that might change their time of use rate by monthly or quarterly as well. So it might not be 2 times a year, it could be 12 times a year that the rate structures change. So you just need to understand that when you go look at your electrical bill. Now, there's other factors that are affecting our utility bill as well. So we have the utility tariff itself, and underneath that tariff, we have a number of things: the cost of energy, the tiered structures, any surcharges that might be involved there, what type of consumer, are you a residence or an agriculture or a business, and then what are the billing periods? Is it a 1-month billing cycle or a 2-month billing cycle, or maybe weekly? So all of those things will affect the price of our utility bills. In this example, we're going to take a quick look at a very simple electrical bill and think about how to read this. So across the top, we have our billing date, and it'll tell often tell the billing period as well. In this case, it's a 1 month. We have a amount of energy used. So if we see the total energy use, 1703. So we're using 1,703 kilowatt hours during that billing period. Then we could look at the cost of electricity. So 1,703 kilowatt hours at 0.1095 cents per kilowatt hour. In this case, this example is in US dollars. So that's 10.95 US cents per kilowatt hour. So we take the 1703 times the 0.1095, means I have 186.48 US dollars is my cost of electricity. Now below that, we have a few other taxes and service fees. We have $29.50 is my monthly access fee. That means that is the price just to be connected to the system, even if I'm not using any electricity. That's the cost to have that energy available to me. We also have other taxes in there, and then we come down to the bottom for our total price of $223 US dollars for this bill. But overall, a very simple bill and a very simple flat rate structure that we see here. We have one fixed price for energy. Now, if we look at a more complex bill, so if we go through this a little bit, we have a longer billing period. Up at the top here, it's 63 days is the billing period. It tells me the rate schedule, which is a residential electric. To the right, we have historical usage. So we can look at how much energy we use this month or the months before. Sometimes we also see what we used a year before or maybe over the entire last year. So that's some historical information that's on there. In the middle section here, this is where things get a little more complicated. We can see we actually have 3 different rate structures. We have a high peak, a low peak, and a base rate. Now, there's also 2 of each of those. In this case, this particular client has a solar electric system that's grid tied. So what it's telling me here is a high peak delivered, which means the utility delivered that energy to the customer. And then the high peak kilowatt hours received means energy that the customer sent back to the utility grid as a credit. And so we're getting an import and an export number here as well. So we can go across there and we get a total used. So how many kilowatt hours were bought and how many kilowatt hours were sold that weren't used in the building at that time. So we get those, and then we look at the same numbers at the low peak and then the base. So we end up with the 3 different tiered structures here, and the different inputs and outputs from the building. Then we go down to the next one. We have what we call demand charges. Demand charges, some utilities put demand charges on residential buildings. A lot of them only do demand charges on commercial and industrial applications. So you need to look at that as well. Demand charge means if I consume, what is the peak kilowatt consumption into that building during that billing period or that month or 2. And what happens is, because the utility has to supply you with all the energy that you can take, they're going to charge you for the highest demand or the highest watts or kilowatts draw that you ever pull from that utility. It means that their job is to create enough power at any given point to supply all the consumers. And they total up all that number, and then they charge you for your highest single point of consumption. So demand charges can apply on utility bills, and they can be a little bit more complicated to understand or to predict. But we need to register that they're out there sometimes. So under there we have demand charges, and then we have energy charges, and then we have taxes, and we come down to a total price of $454.97 for that electric bill. That has a combination of solar and 3 different tiered structures, along with demand charges integrated as well. So this is fairly common in a lot of places in the world to have bills that are more complex like this. Makes it a little bit harder to estimate return on investment for our solar, but if we have all the numbers, those can usually be put into a spreadsheet or a model to try to calculate that. Now, a few other things to think about before we start going out and buying solar is, are we being efficient already in our building or not? And so there's a number of things we can do when it comes to making better choices with efficiency. Things like changing appliances, switching out lighting. So maybe I change from incandescent or fluorescent to LED lighting. If I upgrade appliances, there's a lot of things I can look at. There's a lot of new appliances that are really trying to get high energy efficiency marks. And so there's a lot of new smart technology and control systems, smarter thermostats. So a lot of organizations too that are comparing appliances, so we can see which ones are most efficient, which ones are least efficient. So when I start shopping, I can make sure I buy the most efficient appliances with the highest ratings. We also can see appliances with energy saving settings that are on them, or maybe low consumption settings. Maybe we run at a lower consumption rate and it takes longer to get the clothes done, but it saves me energy over time. So there's a number of different things. We want to start to become a smart consumer and do a little bit of shopping around and a little research before we invest money in some of these different appliances. The other things we can do when we're trying to be more efficient is think about our behavior. How do we use lighting? Am I turning things off? Am I unplugging things? Could I use an occupancy sensor so the lights turn off automatically when I leave the room? maybe I'm adjusting my thermostat a little bit too cold or too hot. And so maybe I can use a little bit less air conditioning by turning that thermostat. Also, if I have time of use rate structures, maybe I want to turn the air conditioning on to cool down the space during an off-peak time, and then try to turn the air conditioner off during the peak time in order to save that high peak cost of electricity. We can do a number of other things too with our refrigeration, making sure that the compressor and the coils behind the refrigerator are clean, so we're not, when they get really dirty, they end up using more energy. Also, when a freezer or fridge gets full of ice, it uses more energy. So keeping those things clean can save us money and energy. And also thinking about things like our water heater. What's the setting? Is it too hot? Am I wasting energy that's just going out through the insulation of the water heater? Various things that we want to consider to change our behaviors to use less energy. Another thing to think about, other than our appliances themselves, is what we call our building envelope. So we can seal and insulate our homes in better ways. And there's a number of ways to create a more insulated home. If we're using a lot of air conditioning or heating, we might be losing a lot of that air conditioning out through gaps in our windows, under our doors, or through old or less insulated windows. So we can do things like using double or triple glazed windows and making sure we have the right cladding type to not conduct as much heat or cold through those windows. We can seal doors and door edges and door jambs so we don't have so much air moving through. We can weather strip or caulk our windows in order to make sure we tighten up that building envelope as best we can so we don't lose all that heat and cool that we're pumping in there. We can do things like window tinting or shades or awnings, or maybe even planting trees in strategic locations to try to keep our homes or our buildings cooler from that sun that comes blazing in and increases our air conditioning load. So it's a lot of things we can do to make our home or our buildings more energy efficient first. And sometimes those energy efficiency upgrades can have a better or a faster return on investment even than our solar. So it's much to be considered there when we're making these investments in our energy. And then the last thing we want to think about is, are we planning for the future? What things might change with my electrical usage as we go forward? Is my family going to grow? And if I have more children, I'm going to use more electricity. Am I planning to add air conditioning or add appliances that I didn't have before? What about an electric vehicle? Might I get a new electric car in 3 years and replace my gas car? And if I do that, how's that going to affect my energy consumption? And so all those sorts of things. Do I plan on doing a big insulation or weather sealing upgrade to my building? What's going to change? Is my electrical usage likely to go up or likely to go down over the next year or 5 years or 10 years? So when we think about the future, we can plan for the future in our solar systems by trying to make some estimates of what we anticipate is going to change with our energy needs so we can really make sure that we're ahead of it when we're designing our solar power system.